So don't spam the chat and all.
Okay. Okay, so I'll start. So basically, this paper is about communication in multi-agent reinforcement learning. So the paper was like written by this lab called Whirl. So those guys have a lot of papers in multi-agent learning, and this is one of their older papers in 2016. So basically, what they try to explain in this is how communication itself is important between multi agents learning, because when you have a game where there are more than one agent, then they need to maximize the shared utility. So they use two approaches in this: reinforced inter-agent learning, which uses DRQN, which is deep recurrent queue networks, and they also use differentiable inter-agent learning, shares, which basically learns directly through gradients. So other than that, they assumed a setting that they called centralized learning but decentralized execution, which I'll explain as it comes. So a very brief view over communication. So they classified it in different ways, and communication is something that is very common in AI. So there are different kinds of classifications also. So the most common one that we need to speak about over here is the cooperative versus competitive setting, which is the most relevant here. And here we are talking about cooperatives. So why exactly would agents need communication? The games need to be cooperative in the sense that there needs to be some incentive for the agents to cooperate with each other, and they need to share information for that. And that also means that the states and the other agents' actions need to be partially observable. If they were entirely observable, then they wouldn't have to communicate, and it would doesn't it won't make any sense to communicate for them. So what these guys try to do is develop something called a communication protocol. So they used a very high level word for that, but as you'll see later on, it's not a very complex signal. So what they achieved with this paper is, maybe it was the first time that reinforcement learning and differentiable communication were used to learn communication protocols using sequences. So basically, they use a lot of deep learning to do this. So quick RL background. So this is basically what any RL problem looks like. There's an environment, there's an agent. Agent act takes some action A, and then it returns some state and reward. So what people did was they developed an algorithm called deep Q learning, and that basically learns the Q values, and it uses neural networks to approximate the Q values. And there's a bunch of stuff that it introduced. So what people did was they added, instead of using feed forward neural networks to approximate the Q functions, they use recurrent neural networks, because in this case we actually need partial observability to be there, and that does not come with the regular ones. So they used the hidden state uh, advantage of the recurrent neural networks to model this. So in multi-agent learning, we talk about the environment as just one single thing, while when there are more than one agent, then we consider a joint action taken, which is basically all their actions, and a joint state. So the state is like our Markov state, and it is going to be same over all the agents. But each agent will receive separate rewards and separate observations, and the observations will be some small function of the state, and they may not be the whole thing. So again, there are two types of multi-agent learning: centralized and decentralized. Centralized means that they learn together, they share information. Decentralized means they're entirely separate. And cooperative competitive is like self-explanatory. So what they try to do in this paper is basically find an optimal communication protocol. So some of the formalities that they defined here was that each agent receives a partial observation, which is somewhat related to the Markov state, like explained over here. There's one state, and each of them receives a separate O. And at each time step, the agent takes one environment action, which acts on the environment, and that is the action that it takes on the environment and receives some reward for that. Now, this action is not visible to the other agents, and it also takes a communication action, which is the action that is visible to the other agents. This they represent using M, and the environment action they represent using U. So this is what they were trying to do. They were trying to establish a communication protocol. But thing is, there's a lot of different ways you can develop it, and there's a lot of different problems that can come. So first of all, there's a lot of it's a very high dimensional concept to define a protocol. So there's a lot of different choices they could have taken in designing it. And other than that, one very important thing is that when agents are communicating between each other, they need to know what kind of messages they need to send, as well as the what messages to understand properly. So both the communication needs to be there, and how to interpret the other person's message should also be important. So because of this, positive rewards are very sparse and they don't come in very often. So in this case, what they do is they use centralized learning and they use decentralized execution. I'll come to that part a little later. So the simplest implementation they used is simply they added the DRQN along with independent Q learning. So independent Q learning is basically they applied Q learning to each of the agents. Each of the agent has its own Q network. Basically, each of them has two Q networks. One Q network is used for the environment action selection, and the other Q network is used for the community action selection. So both of these will use epsilon greedy selectors, which basically means that epsilon percentage of the time they exploit, and with like 1 minus epsilon percent they explore. So yeah, so one thing that they did was that to make sure that the Q networks are not too big, they did not take a very large QNet. Instead, they took two separate QNets, and they're going to maximize over U and then maximize over M, which means that the agent is first concerned about maximizing its own utility, its own rewards, and then it will try to maximize the community reward or the overall reward. So the loss function that is used here, the gradients that are passed, these red lines that are there, these red lines are the gradients that are taken for the community for the environment actions, and there is no gradients of the community actions being taken. So the only communication that's happening in RIAL is basically the community message that's going to be taken. For example, if you look at agent one, so it's going to receive an observation, some O1T from the environment, and it's going to receive the previous time steps message from the other agent. So this agent is going to send some message from here, and it's going to receive it from the top. And this Q network is going to basically process the previous time steps message, the hidden state, and the observation, and it'll pass some action at the end. So that's what this basically does. It does not, however, take advantage of the centralized learning concept, because if you notice, then there's no actual communication happening in terms of sharing parameters or something. So what they decided was they implemented something else called shared parameters. And what they did was they made both of them, both the Q networks, both the agents use the same Q network. And instead, they just added a simple thing by adding the index of the agent itself. So what they ended up doing was they had just one Q network for both the agents, which calculated the environment actions for both of them, and one Q networks for both the agents, which calculated their communication actions. So there were two Q networks instead of using four earlier. So during centralized learning, both the agents use the same Q network to learn, and they update in the same Q networks. But during decentralized execution or during evaluation, they use a copy of the network, and the actual values will be quite different because the observations that they're getting are different from each other, and they will evolve different hidden states compared to each other. So the other algorithm that they proposed was called differential inter-agent learning. So what they did here was basically they took another they call this a CNET. CNET is basically the same thing as a QNet, except the Q network that calculates the communication action is not passed to the epsilon greedy action selector, but it's instead passed to something they call the DRU. So DRU is basically the discretized regularized unit. So what it basically did was this. During centralized learning, they used a sigmoid activator or logistic function, which basically took a normal of the of the communication action and applied some noise to that channel, and then they made it a continuous signal instead of a discrete signal. If you look at RIL, then what the communication action was simply just one action that was passed to the other agent. But in this case, it's some sort of continuous signal instead of a discrete signal. And what they also enabled was that they connected both the CNETs of the agents, and the gradients that are passed here are the gradients of the error as of the communication action as calculated by the CNET here, and it is backpropagated to this agent. So what the paper basically says is that the differential inter-agent learning is trainable across the agents, while the reinforced inter-agent learning is trainable within the each agent. So there's a lot of use of centralized learning happening here. Other than that, what they did was that yeah, one thing I forgot to mention was when they're using this, the regular DKN uses an experience replay, but they omitted the experience replay from both of these things. These are using DRQNs. So the point is, experience replay basically randomly samples past experiences and plays them. But the problem is that it would be non-stationary in the sense that it would replay different memories for both the agents, so they had to keep it stationary. So that is the reason they removed the experience replay, and it changed the performance a lot. Other than that, the original DRQN paper actually used an LSTM, but these guys used RNNs because it was simpler to use. RNNs plus DRUs. So yeah, basically their architecture was this. They just passed the observation, the previous message that they had gotten, the action or the previous action that they had taken, and the agent. They passed it into one single value they called Z. So basically this Z is passed through a two-layer RNN with GRUs, and it finally outputs a Q value for the environment action, the Q values of the environment action, and the messages that they want to use as the communication action. And this goes on over multiple time steps with multiple sorts of sequences. So the final output will give you this simple Q value and communication action. So one of the riddles that they used was called the switch riddle. It's also, you might have heard of the prisoner and bulb problem. So basically the thing is, there is a room, empty room, where you have a guard and you have prisoners. So the empty room has only a single light bulb, and the prisoners are let in one by one by the guard, and they can either choose to switch it on or switch it off. And what they need to do, the final goal, is to find out whether everyone has been in that room at least once or not. So the guard is basically going to take in one person every single day. He's going to tell them that I'm going to take you one in a day. And the person who comes in at the end, he'll have to figure out whether he's the last person to enter it, or whether or not every person has been in that room at least once. So this is a typical game theory problem, and it's used a lot. And these guys, they model it to solve this problem. So in this case, the space for the environment actions is basically none or tell, which means ki none meaning they don't say anything to the guard, and tell meaning ki they tell the guards ki yes, everyone has been in this room before. The communication action is the switch. It's either on or off. So this is called the communication action because this is the only way they can communicate, and this does not matter to the environment because it has no effect on the reward. So other than that, the reward that they get is whenever whichever agent says tell, then they'll all get a +1 if they've all been to the room at least once, and they'll get a -1 if they've not all been, inside the room. So yeah, the observation that is given is basically a 0 or a 1, whether they're inside the interrogation room or they're not. So that's simple. So they compared this with a no communication shared parameters baseline. Basically, if you look at this, the no communication shared parameters baseline is basically where they share a common queue network, but they don't do centralized learning, and they don't communicate with each other, and it's achieved somewhere around 0.7. But they found that the dial and the RIAL algorithms to train really fast, especially when they could share parameters. So this obviously increased in complexity when they increased the number of people, but this is the kind of protocol that it had learned over time when it had n equal to 3, which is basically the number of agents. So this was one of the games that they used. Other than that, they used a game called multi-step MNIST. So the game is simple. There are two agents. Each of the agent has one image given to it, which is basically an MNIST image, and they have to guess the image that is there on their own this thing using the signals that is given by the other person. In the sense, if agent one has a zero, it has to guess that it has a zero by the end of the 4 or 5 time steps, depending only on the M1, M2, M3, M4 signals. So here, the environment action will be any digit from 0 to 9, basically at the end. And the reward that they get is 0.5 for each current guess. So if agent 1 gets 0 here, then you'll get a 0.5. And the communication action in this case will be 0 and 1 for decentralized execution when they're basically doing the evaluation. But when they're learning, they can use a discrete, a continuous form of reward, a continuous form of communication, and it's any number between 0 and 1. So that is one of the games. The other game that they used with MNIST was called the color digit MNIST. Now this is slightly more complicated. Uh, both of the agents have have one image each. So now the images are either green or they're red. So the color of the thing is determined by a digit that they gave it as C, and the digit that's actually there is denoted by D. Now, what the agent is supposed to do is it's supposed to play one of two games. So there are two agents, and they're supposed to play one of two games. They have to decide whether they want to guess the colors of their images, or if they want to guess the parity of their digits. Parity is basically whether the number is odd or even. So the reward function they used was this. It basically shows that the parity, if they attempt to solve the parity of each other, then they earn like double the rewards. And that is what, if you like go through this reward function, then you'll understand. So they compared both of these again with the same algorithms, and what ended up happening was RIAL did not perform any better than the no communication baseline and in the multi-step, and the dial seemed to have increased a lot. So what they understood that centralized learning was something that was much more powerful than not using centralized learning. Even with shared parameters, RIAL couldn't do much better because the gradients that were being passed in the case of dial were a lot better information than RIALs could pass using just a common queue network. So again, if you see the same thing for color digit, then again dial gives a lot more what do you call consistent rewards, and it's better than the other two. So yeah, this is the protocol that they learned to solve this thing. So basically, what one thing that they showed with these results is basically that they learned how to communicate between two agents using just one single value, when it actually takes a lot more values to learn that properly. So what they actually did to learn that was they added noise to the DRU that is there. So if you look at the formula for the DRU, so the DRU is basically the normal distribution of the communication action, and this sigma is basically the variance of that. It's the noise added. They took 2.0 as the maximum one, and they found that it yielded the best results. And what they actually showed here was this. So basically, using sigma that was very little, they understood that see, if you wanted to if you wanted to play the multi-step MNIST, for example, then to actually accurately guess the 10 digits that are there from 0 to 9, you would need at least 4 bits to guess the correct digit. So in this case, what's happening is you're only giving the communication action, which is just one single bit. So you're trying to overfit the information of 4 into just 1. So that causes a lot of problems with the discretization. That is why they added a regularization term, and they found that adding a regularization of term of 2.0 actually gave it much better results when testing rather than on training. So this was one thing that they actually did. Other than this, there was a lot of research done later on. They did research on more complex and larger scale ends. They extended this to more complicated algorithms. One of them was QMIX. So it's a value-based multi-agent reinforcement learning problem, and that actually achieved very good results and actually outperformed all the other value-based methods on StarCraft 2, which is currently one of the best baselines for RL in general. And I think the current state of art is the Google Alpha Craft, Alpha Star. Other than that, one thing that is quite interesting, it's not been done a lot right now, at least not as much as I've seen, is there needs to be research in terms of what exactly this communication actually is telling us, in terms of whether or not these bits that are being transferred can be expressed in terms of human language, key, what exactly are the agents learning, and whether it is just a single number or is it some black box algorithm, or are they using something specific or learning some specific strategies. So that was something that was missing in this paper. They didn't exactly explore a lot about that. They just did more analysis on the results. So yeah, I guess that's it.